Imagine gathering every single book ever written, from the massive archives of Oxford to the small shelves of every local library. Thousands of years of human history, philosophy, and science, all stacked together in one place. Now expand that collection to include the entire internet. Every blog post, every news article, and every digital page ever published, all converted into physical print and added to the mountain of paper. But here, the scale creates a problem. More than half of this information is effectively noise, filled with duplicate pages, misinformation, and corrupted text that offers no value. To make this data useful, it is pushed through a massive digital filter. This system identifies and deletes the garbage, leaving behind a purified, concentrated stream of high-quality human knowledge. This refined data stream is then fed into a supercomputer, providing it with the absolute best examples of how humans think, write, and communicate. This filtered ocean of text is the bedrock. It is the essential foundation that allows models like ChatGPT to understand the world before they ever say a single word. Having the data is only the first step. To become intelligent, the machine must undergo training, an intense computational process requiring thousands of advanced GPU processors running for months at a time. During this process, the machine doesn't read the text in the way a human does. It cannot see words. It can only process numbers. The system translates every word into fragments called tokens. Each is assigned a unique numerical value, turning sentences into math. By analyzing billions of tokens, the AI maps language patterns, learning that after ocean, deep will highly likely follow. Through this mathematical lens, the AI builds an internal model of human logic, a universe of numbers that allows it to predict how concepts are connected across every field of study. This mathematical universe is housed within a complex architecture called a neural network. While your brain relies on billions of neurons to think, a modern AI model functions through trillions of digital connections called parameters. The second you ask a question, the model shatters your prompt into thousands of different tokens to be processed simultaneously. Those trillions of internal parameters react instantly, weighing the context and relationships of every word to determine exactly what you're looking for. This lightning-fast activation across a massive digital web is what creates the illusion of a thinking mind. It's easy to think that the AI is just searching a database and copying an answer, like a search engine. But the machine isn't looking anything up. Instead, it plays next token prediction. It calculates the statistical odds for the most logical starting word. Once generated, it adds it to the sentence and recalculates. It builds the answer one token at a time, in real time. This process is similar to the autocomplete on your phone, but scaled to such a massive level that it can construct complex arguments. Because it generates responses from scratch rather than copying them, the AI can produce original code, creative stories, and insights that have never been published before. But there's a catch. If the model learned from the entire internet, why isn't it as toxic or biased as the web can often be? After its initial training, the AI is effectively raw. Its outputs are chaotic and unpredictable, based on the unfiltered data of the internet. This is where engineers apply reinforcement learning from human feedback, or RLHF. An army of human trainers interacts with the model, asking it questions and reviewing its responses. If the AI provides a dangerous or unhelpful answer, it is penalized. If it is helpful and safe, it is rewarded. Through thousands of these interactions, the model learns human preferences, turning a wild mathematical engine into the polite, helpful assistant we use today. We have moved from scanning the world's libraries to building trillion-parameter networks that can predict human intent in milliseconds. This capability has scaled so rapidly that these models now function in our pockets, changing the way we solve problems every day. Because these models excel at predicting patterns in any sequence, researchers are now treating the complex code of human proteins like a language. By predicting the next token in a molecular chain, the system can help design specific compounds for new medications. This same architecture is being applied to massive streams of astrophysical data. Instead of words, the system scans light signals from deep space, identifying orbital patterns and cosmic anomalies that would be impossible for human researchers to find manually. We are moving into an era where human inquiry is paired with a machine that can navigate the sum of our recorded history. We are seeing the first results of a world where our knowledge finally moves at the speed of our thoughts.